What comes to mind when you think of a jellyfish? Oftentimes, people would think of it as an animal that moves slowly, looks simple, and feels soft to touch. But have you ever wondered if there is anything special about its movement? Before we dive deeper into this, let's first get to know the moon jellyfish. The moon jellyfish is one of the most common types of jellyfish in the Philippines. Its body is shaped like an upside-down bowl with an opening at the bottom, and it is also soft enough to bend in different ways. With this soft body, it moves in 3 stages. First, the opening of the jellyfish body starts small. This stage is called contraction. Next, the body takes in water like a vacuum, which makes the opening wider. This is called transition. Lastly, when the body is already full of water, its opening is at its widest. This stage is called expansion. Then, starting from expansion, the jellyfish does the reverse. Going back, the body releases water, causing the opening to be smaller and forcing the jellyfish to move forward. This concept of a force being applied on an area is called pressure. Now, when all of the water has been released, the jellyfish opening is at its smallest and it has returned to the first stage. This cycle then repeats on and on. So, now that you know how jellyfishes move, we now explore how these steps affect how water moves around the jellyfish. One way to know this is through using advanced computer programs called Computational Fluid Dynamics or CFD. These programs can copy the movement of the jellyfish and the water around it. Afterwards, it can compute the characteristics of the water movement, such as speed and pressure. These are characteristics that we cannot easily compute by observing using our eyes. However, only a few people have used CFD before to study moon jellyfish, leaving much to explore on this topic.
Good day. We are David Magnaye, Bianca PERALTA, and Francesca TUMANENG. Today, we present our study entitled Computational Fluid Dynamics of Solid Bodies inspired by the movement of moon jellyfish or Aurelia aurita. This study has the main goal of studying the effects of the moon jellyfish movement on the water around it using CFD. To be more specific, the speed and pressure of the water were studied. This study can help scientists and experts across different fields by providing new knowledge. For example, zoologists can use this to know the moon jellyfish better, physicists to understand the nature of the water movement, and engineers to apply this in buildings and structures. The study was done in multiple steps. First, videos of a moving moon jellyfish were taken. From these videos, 3 screenshots were taken, which show the 3 stages of jellyfish movement. Then, the outline of the jellyfish in these shots were made into 3D shapes. For this study to be simpler, these 3D shapes were made symmetrical. Afterwards, these shapes were put into a CFD program. To imitate the environment of the moon jellyfish, the starting speed and pressure of the surrounding water were based on moon jellyfish studies. Once the CFD program has copied the water movement, it computed the resulting speed and pressure values. Since water goes in and out of the jellyfish opening during its movement, the program computed the results in 2 directions, one going in the opening and one going out. This was then done to all 3 moon jellyfish shapes. Finally, the results from each moon jellyfish shape were produced in the form of contour plots and were visually compared to each other.
You can think of contour plots as images formed by the CFD program with different colors surrounding the 3D shape. The warmer the color, the higher the value. So red has the highest value, while blue has the lowest. When water is moving towards the opening, all contour plots have higher speeds at the back of the 3D shape as seen by the green color. Pressure is also lower at the back as seen by the blue color. This is the same as what happens with jellyfish expansion in real life. On the other hand, when water is moving away from the opening, all contour plots have higher speeds near the opening, while pressure again is lower. This now is the same as what happens with jellyfish contraction. If you have observed, all the contour plots had higher pressures in places where speeds were low, while lower pressures were seen in places where speeds were high. This follows a physics concept called Bernoulli's principle. Something special was observed in the contour plots. In the middle of each plot, an area of water was seen to be rotating with just enough speed. This area acted as a barrier which the rest of the water followed. This means that the curves of the 3D shapes affect how the water moves. To summarize, the 3D shape showing the expansion step is the best in blocking water moving towards the body and in allowing water to flow when it is moving away from the body. The 3D shape showing the contraction step is the best in allowing water to flow when it is moving towards the body and in blocking water moving away from the body. These findings prove that CFD can be used in studying complicated animal bodies and the behavior of water around them. Although the study was successful, it can still be improved in some ways. First, more screenshots can be taken from videos of a moving moon jellyfish, or the 3D shapes themselves may be made more rounded. Second, the study may also be tested in real life. Finally, more advanced computer programs may be used. Now you know what the moon jellyfish is and how it moves.